So let's hit it. So it's our pleasure today of having Marty Juric, who is leading the data management team of LSST, and he will talk more about it. Luis recommended this talk. Or a related talk that he saw last week on FirmLab on the DES LSST meeting. And so, please, go on, Mario.
Thanks, Ricardo, and thank you, Luis, for inviting me to give this talk here. It's going to be similar, but slightly modified from the one I gave in FirmLab a week ago. And if, given this is being done remotely, if there are problems at any point in time, please do interrupt me. If you can't hear what I said, or if you want me to repeat something, or if the slides are not showing up, let me know, and then we'll try to make it better. So this is going to be a talk about LSST data management, about what LSST, the Large Synoptic Survey Telescope, is, what we do, and what data management does within LSST, and what kind of data products we're going to produce. So what LSST is, it's a planned, wide, deep, and fast survey telescope. So beginning in 2022, this 8-meter class telescope that will be in Chile and Cerro Pachon will repeatedly begin imaging the sky for about 10 years. And we'll do that continually, covering the sky, covering the visible sky once every 3 days. But the right way to think about this system really is not as a telescope. It's really an integrated survey system. It is the observatory, so the mirrors, the dome, and everything else, all the hardware, the telescope, the camera, and the data management system. All of them will be built to support the LSST survey. There is no traditional PI mode or proposals or time on this telescope, but what we're going to do is we're going to build it, we're going to attach computers to it, and we're going to survey the sky continuously and automatically. So in that sense, LSST really isn't a telescope. It's a survey. It's a database. The ultimate deliverable of this project is not the telescope, it's not the instruments, it's really the fully reduced data. So what you get out are catalogs and images, and that's how science will be done. The interesting thing is that this data will be largely public. So all of LSST data, including images and catalogs, will be available with no proprietary period to anyone in the United States, Chile, and international partners. And from what I understand right now, there are discussions underway to have Brazil join as one of those international partners. Alerts to variable sources, so I'll talk about that in a moment, but we were going to be detecting what changed in the sky virtually in real time. Those will be available worldwide within 60 seconds using video event or similar standard protocols. And then third part in this open data, open source community resource idea is that our entire data processing stack, our entire software stack will be free. Free in the sense of GPL, so open source, you'll be able to download it, compile it, modify it, do whatever you want with it. Now, from the astronomer's perspective, as I mentioned, the LSST is not a telescope. It is a big database with 3 kinds of data products. Level 1 data products are things that we measure and do every night. So this will be largely a stream of about 10 million time domain events per night that we will detect and transmit to distribution networks within 60 seconds of observations. So what that means, anything that's changed in the sky, in the sky that LSST observed, we'll know within 60 seconds and send it out. This same data stream will also produce a catalog of orbits for about 6 million bodies in the solar system. Now, on a longer cadence, every year, we plan to reprocess all the data that LSST collects, do it more carefully, more methodically, with better calibrations, and produce a high-quality data release that will ultimately consist of about 40 billion objects. So that's roughly 20 billion galaxies and 20 billion stars. Then 7 trillion observations of those objects, and about 30 trillion measurements. So basically, every object will be observed around between 800 and 1,000 times. All of these will be processed annually, so every year we'll process everything from the start of the survey, and they'll be accessible through online databases. In addition to these catalogs, we'll also provide deep co-added images. So if you have something that depends on looking back at the image data, if you have some piece of science that requires image data, you will be able to do that with LSST. Now, part of the reality with LSST is that it's going to be huge, just in terms of data volume. So one of the things we're trying to enable is, instead of requiring everyone to download everything to their home institution, we are going and resources at our data center to enable user-specified custom processing and analyses. So that is what level 3 is. Think of LSST as a cloud-based service. You'll be able to upload your code to the computers where the data resides and get your work done there if you don't have the resources or don't want to download the data to your home institution. So in addition to that, we will provide both software and APIs to enable such kinds of analysis and writing of analysis codes. So that is in a nutshell what the data products that are going to be coming from LSST are. And I'm going to go into a little bit more detail on each one of these in the next couple of slides. So level 1, as I mentioned, are transient alerts. These are alerts to anything that has changed in the sky compared to a deep image of the sky built using observations collected over the previous year. So LSST computing is sized for about 10 million alerts per night on average. LSST will be collecting about 1,000 images per night, 1,000 visits. So that comes out roughly to about 10,000 alerts or 10,000 things that changed on every exposure. And just to remind you, LSST on average observes every 39 seconds. So every 39 seconds we will be streaming all the data directly from Chile to the US. We'll be processing it and we'll be putting it out, and we'll be publishing the results of that processing in form of alerts. Now with each alert, we're going to measure and transmit its position. So where has something changed in the sky? Its flux, size, and shape, so that downstream users are able to know what's happened. We will also cross-correlate it to the database from our data release processing, so from what happened before. So we will know for each object if it already appeared, and if it did appear, what are its light curves in all bands. And we will broadcast that with the alert. We'll also broadcast some variability characterization, and importantly, we'll broadcast cutouts centered on the object, so little images that allow you to run, that allow the downstream user to run, to either look at the object visually or run some of their own machine learning algorithms or measurement algorithms on the data stream in real time. So all of this will be streaming out of the LSST data center, and to give you an idea, these streams are going to be on order of 4 gigabits per second when we start putting them out. So as you can tell, one of the very important things that we need to work on as a community is how to filter this alert stream, because out of the 10 million alerts per night, not all of them are going to be equally interesting. There may be only 1 or 2 that are worth following up with even larger telescopes, like the GMT or the TMT. And this really is a challenge for the next 8 years to figure out how to do that efficient filtering. Now, on an annual basis, we will reprocess all the data to produce well-calibrated, consistently processed catalogs and images. So this is very similar to what you get from the SDSS or from DES. These are catalogs of objects, detections of difference images, etc., that are all put into a database and made available. So these will come out every year, except for the first year of data. For the first year of data, we're going to do 2 data releases, one for the first 6 months of data and the second for the first 12 months of data. The idea there is that when LSST goes on the sky, even in the first 6 months of data, there'll be so much interesting science to do, so that we don't want to delay it any further. The second reason for doing this is that we realize that we're not going to be perfect. And putting data out sooner allows the community to test it, to use it, and to tell us what may have gone wrong. So we can fix that and make it better for the next data release. Now, one important thing to point out is that all the data is going to be processed in each data release. So we will, in data release 10 or in data release 11, at the end of the survey, at the end of the 10 years, we will process in 1 year, 10 years worth of observations. Our projected catalog sizes, as I said, are going to grow to about 40 billion objects and about 30 trillion measurements. But the interesting thing is that that growth is not linear. Even after the first 6 months, we'll already have about 20 billion objects in the database, so almost a half. And if you think about it, what's the reason for that? Part of the reason is that the galaxy is finite. We run out of stars. So what happens there is LSST sees deep enough that we're actually, even in the first year, able to see through to the edge of the galaxy, if you will, and collect most of the stars we'll see in the entire program. So this is adding a little bit more detail to what level 2 data products are going to be. As I said, we're going to have 2 classes, catalogs and images. So for images, we're going to put out processed visits. We also call these calibrated exposures. These are basically images with instrumental signature removed, with backgrounds determined, with PSFs determined, with 0 points determined, with WCS determined. So these are ready to be used by downstream scientists to do their science. We'll also produce coads, deep coads across the entire survey footprint. But I think where most of the science is going to be coming from are the catalogs. And for the catalogs, we're going to have 3 classes of measurements, or 3 classes of objects, if you will. One catalog is going to be a catalog of sources. So these are sources detected on each exposure. So if I take an exposure on the sky and just run Sextractor on each individual exposure and put that in a catalog, that is what we would get. And of course, we wouldn't be running Sextractor. We're going to be running code that we're writing right now, and I'll talk about that soon. Catalogs of objects are going to be objects detected on multi-object data. So these are going to be objects detected on deep coads. We'll build a coad that will go much deeper than individual images. We'll detect on that coad, and that is what this catalog is going to be. One of the interesting points there is that we're not just going to measure the most likely magnitude or maximum likelihood magnitude of the object, or even the expectation value for its flux or for its shape. We plan to be measuring posterior samples. So we plan to be characterizing the posterior for all those measurements, so that in effect you will be getting something like not 1 catalog but 200 realizations of the same catalog. And this is extremely important when trying to do science that fundamentally depends and that is very sensitive to systematics. So the prime example here is really dark energy science and weak lensing. So these are the sort of things that are being done on DES, or that are being considered for DES today as well. Now, the third thing is going to be catalog of force sources. So when we detect objects on deep images, we will have that catalog of about 40 billion objects. Most of those objects are not going to be visible in individual exposures. But nevertheless, if you know where they are, you can go and measure at that position. Because even though that measurement will be at a reduced signal to noise, it is still statistically useful information and can be incorporated in your analyses. So we will do that, and we will build catalogs of force sources for every object detected in the coad and every object detected on image differences. Now, all of this will feed into users' analyses. So all of this will be done, will be used to do science. And one of the things we realize, actually 2 things that we realize, are that A, not all the data products that we produce, or the data products that we produce will not enable all the science, just because there are so many things that one can do. And B, to create new data products, it will be useful to enable the users to run codes in our data center, so that they don't have to download the entire multi-petabyte data set. So this is what level 3 is about. The examples of uses where you may need to produce new data products are things that are not enabled by level 1 and level 2 processing. So one example is reprocessing images to search for supernova light echoes. If you think about what these light echoes are, these are very diffuse structures in the background light on images. Our catalogs, by their nature, are fairly localized, point source and extended source oriented. So for these kinds of things, you really need special processing. The other example there is characterization of diffuse structure. For example, the interstellar matter. If you look at those beautiful images in the infrared of the galaxy, you'll see lots of things that aren't stars or external galaxies. This is the sort of thing that requires special processing. Extremely crowded field photometry is another example. So in the centers of globular clusters, it is very difficult to get the right photometry with general purpose codes like the one we're writing for LSST. Someone may want to run their own code to do that. And then there are custom measurement algorithms. For example, you can imagine developing a specialized algorithm to measure a particular quantity that you're interested in for your science. So to enable level 3, we're building databases that the user will be able to use, something like MyDB in SDSS and CAS. We'll enable computing at the LSST data center, and we'll make the LSST software stack available to the end users. So you can download it, that you can build the tools for additional processing on top of our stack, and then upload it to the data center. So in all of this, I've been saying we many times, and now I'm going to spend a couple of minutes talking about who we is. And it is primarily the LSST data management subsystem. So LSST data management subsystem is about a third of LSST project. It is the people and machines who take the images after they're read out from the camera and then process them all the way to the delivery to the user. The LSST data management roles are there are three main LSST data management roles. One is we're the ones who need to ensure that no data gets lost. We need to archive it. We'll need to receive that stream of images and make sure that it's in a safe place. Secondly, we need to process all those images into data products, detect and alert on transient events, and then once a year create and archive a data release, and then publish it. Publishing means making all the LSST data available. We plan to do that through both machine and human interfaces. So you'll be able to either go to a website or fire up an app or whatever it is going to be the best way to do it in 2020. But you will also be able to point your machine, your computer, your program to our data center servers and do the analysis that way. That is actually going to be something very important in the age of LSST because most of us are not going to be looking at those images. We'll be teaching the computer to do it for us. Our system is very distributed. The headquarters of data management as well as LSST is in Tucson, but the telescope, as I said, is in Chile. However, all the processing will happen at NCSA in Urbana-Champaign at the Archive Center at the National Petascale Computing Facility. And to be able to do that, we need to have fast, dedicated networks. So right now we're planning 2 redundant 40 gigabit links from La Serena to Champaign, Illinois, making it possible, making available to us 80 gigabits of bandwidth where everything works, and adding redundancy. So if one of these links gets cut, we can still do the entire survey through the other link while the link that was damaged gets repaired. At NCSA, we will have a fairly big data center. We'll have about a petaflop worth of computing. What I'm showing you here is actually the image of a blue water system at the room where we're going to house our computer. This is a computer that sits there right now that already has a petaflop of power today. But to give you an idea, it's roughly as expensive as all of the development of data management and all of our computing from now through the end of construction 8 years ago. So we will definitely benefit from Moore's Law. By the time we're on the sky, we will have a system like this at NCSA as well. Now, the important thing that runs on a system like this are the science programs. So things that take the images and turn them into catalogs, turn them into measurements that we can use to do physics with them. And this is what we call applications. So applications really carry the core scientific algorithms that process or analyze raw LSST data. As I said, we do a variety of processing, and we built all of this on a layer called the applications framework that allows us to write all these codes in higher level languages, and I'll talk about that a little bit more in a second. As you may have noticed in that previous image, the applications are sandwiched between two levels of what we call middleware. One is on top, the middleware that controls the execution of these pipelines in hundreds of thousands of cores. So we need to be able to run this at scale to process, as I said, years of LSST data. That will require computing clusters scaling over thousands to tens to hundreds of thousands of cores, and that will require some code to make sure that all of this is running with fault tolerance, with robustness, and with orchestration that we need. On the bottom of that is another piece of middleware that is there to isolate the pipelines from details of underlying hardware. And one of the things you need to realize about LSST is that it's going to be a project that will last for about 10 years. So we need to make sure that our applications do not extremely depend on whatever hardware there is in 2020, because in 2030, the hardware will have changed. So we don't want to be wiring any assumptions about the hardware in our science codes. That is what this middleware layer does. It isolates the pipelines from the details of the underlying hardware. Once the pipelines do their job and complete the processing, the results are catalogs and images. And then our next step is to organize them and to present them to the users, to the scientific community. All the data, all the catalog data is going to be managed in a large distributed database. We're building something called QServe that will do this. This database is built using XRD and MySQL as key components. It will also be open source, so it will also be free software, and you will be able to download the database as well as the data in it. The other thing we're doing is we're building science user interfaces to enable quick access and analysis of LSST data. So what I'm showing you here on one of these images is an example of a prototype user interface that was built at IPAC and loaded up with SDSS data. These interfaces will be evolving through the next 8 years or so that by the time LSST goes on the sky in the 2020s, we will have something that's modern and useful at the time. And then the last thing I was going to say about the data management system is that you may have noticed that there were many, many logos attached to various pieces of the software and hardware that I talked about. And the reason for that is that this is a very distributed team. We're distributed over six institutions. Our idea is that this is going to be one of the most complex pieces of astronomical software ever written, and we needed to go where the talent is to build a distributed team rather than trying to gather everyone at one place. And so that is what you're seeing here. We are really coast to coast from Princeton in the U.S. to SLAC, from Princeton in the East Coast to SLAC on the West Coast, and then Tucson and NCSA in the middle. So that, I hope, gives you some overview of what we plan to do or how the LSST data management system, what the data management system is and how we function. And now I'm going to spend the rest of my talk talking about the software, the LSST software stack, the science pipelines, the middleware, the database, and the user interfaces. So this really is the core of what we're trying to do to process LSST data and make sure that one can do science with it. Our goal, our mission statement, is to enable LSST science by creating the well-documented, state-of-the-art, high-performance, scalable, multi-camera, open-source, OIR, survey data processing and analysis system. Now, this really sounds like a mouthful, and it's a long sentence with lots of buzzwords. But I assure you, we've actually spent a lot of time thinking about this. A well-documented system is required because otherwise there is no way for users to use it. State-of-the-art algorithms, new algorithms that we have to invent are required so that we can reach the performance that is needed to discover the nature of dark energy. We need to do this at a very high level of performance, just because of the computing requirements that are put on us given the volume of the data. We need to make this scalable. This piece of software needs to run on everything from a laptop to a 100,000 core cluster. Otherwise, it won't be able to help the users do their own analyses, that is run on a laptop, or it won't be able to do the data processing for LSST, that is run on clusters. We need to make sure the system works in multiple cameras. The reason for that is there is no way to know whether your software system works unless you test it on real data. We won't have real data with LSST for another 6 years, and therefore we need to test it on existing surveys like Subaru, like DES, like SDSS. So we need to make sure that this software stack can work on multiple cameras. We want to make it open source. Part of the reason for that is that allows us to use the existing body of open source code on the internet to make our lives easier and to build a more robust system. But an even better reason for that is that we really want to make this system that will live beyond and far longer than LSST itself. There is no point in developing a data processing system that will be super specific for just one survey. This is, if this is made right, it can be something that can be adopted by other surveys as well, and making it open source is a huge step in that direction. So going into the next level of details, and I apologize for all the numbers on this slide, but this is just sort of to give you an idea of what is in the LSST software stack, what kinds of data pipelines. So to first order, basically it's everything. It is processing of single frames, it is image differencing, it is co-addition, it is estimations of PSF, and finally it is the toolkits to enable the users to build their own pipelines on top of ours. Now, how do we go about building this? There are already many very successful pipelines out there. A prime example are the Astromatic tools that include Sextractor, BSFX, Swarp, etc., that I'm sure you're all very familiar with. We have looked at this a couple of years ago and decided not to directly adopt any of those tools, not to adopt the code, but to transfer know-how, really. There are many reasons to do that, but I think that the key reasons are that none of the tools in existence right now have been built to run as a high-performance system, to be maintainable over decades by teams of over tens of engineers and scientists, and to run on a variety of hardware. So instead, we made a decision to transfer scientific know-how, but not the code. Instead, we wrote the code ourselves. So LSST software stack is largely written from scratch. It's written in Python unless computational demands require the use of C++. So we only use C++ for something that needs to be fast and cannot be done efficiently in Python. But we make it available to Python via SWIG. So everything in LSST is a Python module. We do not run separate executables and then communicate via files. We're actually able to do end-to-end processing with Python modules. And ultimately, that is something that will allow us to have such a high level of performance. Everything is modular. As I mentioned, virtually everything is a Python module. Right now we have about 60 packages. Actually, now that I'm saying this, that number is probably out of date. The number of packages is growing every day. They're all in Git repositories. We use Git for version control. For package management, we use EUPS, the same tool that is used on DES. And for our build system, we use SCONS. So to put those modules together, this is sort of what our system looks like. On the bottom, we have many external C++ and Python libraries that we've just adopted. So you'll see the usual suspects there, like Boost, Eigen, or FOTW on the C++ side, and then things like NumPy, Matplotlib, or Bifits on the Python side. Then on top of that, we have the high-performance software layer written in largely C++. That is the red boxes. And then on top of that, we build the actual algorithms. We build the science pipelines. So instrumental signature removal, source detection, co-adding, all of that gets done in Python. The current state of this code is actually much further along than you would imagine. So LSST hasn't officially started construction yet. We're going to start in July. But there has been already a 7-year prototyping effort. And right now, we're at a point where this is a rapidly maturing state-of-the-art astronomical data reduction system. We're basically at SDSS level of quality in terms of reductions. And we test this code every couple of months. Most recently, we tested it by building coads using SDSS Stripe 82 data. And it's also used in operations on HyperSuprime Chem survey on Subaru. So that is an actual real-life survey that is happening today that is using our prototypes to do science. And that is quite impressive for a software system that's not supposed to exist in its final form for another 8 years. So since an image is worth a 1,000 words, I thought I would show you this one. This is SDSS Stripe 82. This is a small piece of SDSS Stripe 82 processed with LSST data. That is, this is a coad built with LSST data, with LSST software. And if I remove the text so that you can see it better, what you see on this image is the M2 globular cluster in the bottom right. But you also see, note the diffuse structure that spans through the image. Those really are those really are galactic. That really is galactic ISM. You can even see how its spectrum changes, how its color changes from bottom to top. And this is the sort of thing you get with LSST Stack with the new algorithms we built in that ensure that this kind of diffuse structure is retained in the images. Another example of this are streams that around external galaxies that one can detect in that Stripe 82 reprocessed data. So I'm not sure if you can see this on your projector over there, but this galaxy has 2 streams that are sticking out of it, mostly to its left. And we found this one by just panning through the images reprocessed with LSST code on this website that's listed in the bottom right. And you can actually go to that website. I don't believe it has a password or anything, and see it for yourself. And the third thing is, this is a little bit more quantitative than the previous 2 plots. It's the quality of photometry that comes out. So what I'm showing you here are the color magnitude diagrams. Essentially, the stellar locus, or the width of the stellar locus, just shown in a better coordinate system, shall we say, or a better combination of colors, as defined by Ivazic et al. 2004. What is interesting here is how tight this relation is. So on the left plot, you'll notice magnitude is on the y-axis and color is on the x-axis. And note how tight that width is all the way down to about 22. If you do this with single epoch SDSS data, you will notice this color relation becoming much wider once you pass 20. So what we're showing here is that we're going much deeper with LSST Stack by measuring on the coads. So these are the kinds of things that we have now, and these are the kinds of things that actually is available now to anyone who wants to install it and learn how to use it and use it. LSST software, as I said, is going to be open source, but what I should also say is that it is open source right now. To install it, it should be as easy as the 2 commands that I'm showing up there. You run that, you wait for anywhere between 20 minutes or a couple of hours, depending on how fast your machine is, and you get the LSST software stack installed. There is an early draft of the user's guide at the address shown over there, and there's a new release of this stack every 6 months. But before all of you stop listening to what I'm saying and run off trying to build the stack, I need to give you a warning. And the warning is that this is still not a finished, polished, ready-to-use end-user product. And before downloading, you need to make sure to read the LSST DMStack frequently asked questions page, or otherwise we don't guarantee that this stack won't destroy your computer or eat your puppies, like this baby over there. So the key point really is that these are prototypes. We've just built them. We still have almost a decade to go to build them to perfection. And the documentation is poor, the code is unsupported, and the code will not work out of the box for cameras other than LSST and SDSS. So if you want to use this, you should expect a fairly steep learning curve. You should expect to write some Python code, and you should expect to interact with LSST data management team quite often. Now that I've scared you away from using this stack, let me say this. The LSST stack, the way we build it, is reusable and general purpose. So ultimately, we believe that this will be the thing to use to process your data even on a casual basis, but especially if you're building large surveys. There are tremendous opportunities for using stack components in existing and future data sets. While there is more work ahead, as I mentioned in previous slides, this thing is becoming a state-of-the-art. It's going to be well supported. It's going to be code-based that's going to live for 25 years through LSST design, development, and finally operations. So there are possibilities to use it to do cutting-edge science on SDSS, on CFHT-LS, on DES, on all these other surveys. And it's a good basis for analysis for building analysis frameworks. Another thing to sort of notice, and this is especially important if you're thinking about how these systems, how much these systems cost and how they're funded, this is really leveraging $100 million investments in large survey data management. So if you are building a survey of your own, there is no point for you to go spending again the money at those levels when you can reuse something that's already been done, something that's already been paid for. So these are really the promises going forward for the LSST stack, that not just it can do the LSST, but it can help other surveys as well to make their job easier, to make it possible for them to reuse the pieces of LSST code and get better science out sooner. The benefits of all of this feed back to LSST as well. We get more users, we get less bugs, we get better understanding of what we're doing, and ultimately we get to a shorter path to science with LSST. So we've already started this kind of community interaction by opening a site on GitHub where we invite people to put up third-party software delivered or derived from LSST code base, or you can just create your own GitHub site and fork our code there. So to start closing this talk, I thought I would end with a list of links and where you can find more information about both LSST data management and about LSST software stack. So there's a page there that tells you how to use the stack to process simulated images, then to process SDSS data, and then there are various tutorials on developing with LSST stack components. But the most important thing I want to point out here is if you're interested in LSST software, you should really join our mailing list. So the mailing list listed at the bottom, LSST DMStack users, is open to anyone. Most of us in data management are subscribed to it as well. It is intended to be a sort of community list for people who use the DMStack to communicate and to talk to us. And right now, in case you're worried, it's not actually a high-traffic mailing list. There are a couple of emails per month or every week. So if you're curious about it, I would propose you subscribe to it, and just, if for no other reason, just to be in the loop of what's going on with LSST code and LSST data management in general. So I will end there. I will leave you with this final summary of what LSST is, and I'll take some questions. Thank you. And if you don't mind, I'm going to.
Okay, thank you, Mark.
Thanks, Ricardo. And I'm going to turn off screen time for a second so that I can see you again.
Here's Bruno. I have two questions. The first one is, does LSST intends to match his own catalog with another catalogs like the Simbad or other things to identify the sources? How you plan to do that?
So we don't plan to do it systematically for all catalogs that are out there. We plan to do it for major catalogs, partly to enable our data processing. So you could expect that a copy of SDSS is going to reside next to LSST and be matched to it. Most likely DES and